All right, so arc length, we'll start off super basic and then get super hard.
Awesome.
Great.
So if you have 2 points and you want to find the distance between them, what do?
y2 minus y1 over x2 minus x1.
That would be slope,
It's slope.
but that's the right idea. So
Like,
bottom line is you just use the Pythagorean theorem.
Oh, a squared means that stuff.
Yeah, so you find the length here, we call that A. Find the length B there, and then over here, that's our C. So A squared plus B squared equals C squared. C is the length we want, so we have to take the square root, right? So C would just then be the square root of A squared plus B squared. So we're going to apply the Pythagorean theorem to things that aren't straight and see what happens.
oh dear.
So the distance formula is just the Pythagorean theorem. Now you probably learned a more complicated version of this for distance, where you call this x1 and that x2. This would then be y1 and that would be y2. So A happens to be x2 minus x1, and you've got to square it. B happens to be y2 minus y1, and you have to square it. Add them up, take the square root, which is just an application of the Pythagorean theorem, right?
Yeah.
Okay, so this is the hard version. That's the easy version. I'm going to kind of stick with the easy version today. Okay, so let's apply it to a more interesting curvy thing. This curvy thing here.
What? Isn't the reason why I had the harder one was because we couldn't take, because it had to be a right angle triangle to
No, I mean, they're both the same thing back here. It's just,
and that would be used for not right angle triangles?
no, the bottom line is this depends on that, which depends on a right triangle. You can only apply that if you have a right angle. Yep. So the same thing's going to apply when we start to play with curves. So what we can do is, if we wanted to find the length of this funky blue function sitting in the background there, we could just pick a bunch of points on it. Like this one and this one and this one, and then connect the dots, and then find the length of each of those segments. That's going to be an approximation of the length of the curve. Okay. The distance between these guys right here, that's what we call our delta x. So if we just let delta x get smaller, then we'll have more intervals, right? So n gets bigger, n being the number of segments I have here. Then we're going to get closer and closer and closer to the actual arc length. Okay. Now, if you want to add up a whole bunch of things, you use a sum, right? Yeah. If you let the number of things in that sum go to infinity, which means there's some little interval that's going to 0, then it turns into the definite interval. So all we have to do is figure out what these things look like in general, and then we know the definite interval for it. And so we're going to turn the sum of these lengths into an interval. So now we're just going to zoom in on one of these. So zooming in, so let's say this is my curve there, and I zoom in and I pick this x value right there. Then I get a situation that looks kind of like this. There's my delta x, there's my delta y, and then for some reason arc length is given the letter s. I can never remember why.
Theta equals s over r, right?
So we're going to call this a change in the arc length, or a delta s.
I know that's the equation.
So a change in our arc length here, a little chunk of arc length, is going to be equal to delta x squared plus delta y squared, it's y. And we take the square root of that because we just want that little change in s right there. I know, that's what I said. Same thing as before. Now we're going to have a whole bunch of these. So we're going to add them all up. So we're going to have a whole bunch of these delta s's added up. right? Each one's going to be a little different, so we can call them delta S of I. I goes from 1 to n, breaking up our interval, right? Just like we did with areas, except instead of area, we're just looking at the little arc length at the top. Very similar idea. And if we take the limit of this as n goes to infinity, then we're going to end up with some integral. And we have a little more work to do before we can get that integral. So there's a couple different ways to look at it. One way is to look at the rate of change of the arc length. So that would mean looking at the change in the arc length compared to the change in, say, x. So that would be the arc length changing as x changes. Well, my arc length is this crazy square root. Delta x squared plus delta y squared. And now I'm dividing it by delta x. And it turns out that right side cleans up dramatically, because I can rewrite delta x as the square root of delta x squared. Right, because then the square and a root cancel each other. Yeah, so that's that same denominator there. And so now I have a square root divided by a square root, and square roots work nice with division. So I can say, hey, that's just the square root of that fraction. And the delta x squared doesn't cancel completely. What happens here?
1 plus the...
Yeah, so on one side, I'm going to get delta x squared over delta x squared, which is a 1. But then I'm going to get delta y squared over delta x squared. So which I'm going to write as delta y over delta x squared. So it turns out this is the rate, the approximate rate of change of the arc length. Now, if we do a little differential algebra, then we can just bring that delta x over to the other side. What is this starting to look like? An integrand, right? Because this is in the limit, the delta x's are dx. So back to the other page. So we just morphed that thing right there. And when we take the limit, the delta x and the delta y turn into dx's. So what we're going to get is 1 plus something squared dx. So what does, if I take the limit as delta x goes to 0 of delta y over delta x, does anybody know what that turns into?
Delta x.
No. What is that? What is it?
1 is delta y. No.
That's the definition of f prime of x. Change in y over change in x, right? Let the bottom go to 0. D delta x is our h. Way back from Calc 1, this turns into f prime of x. So that's what goes right here, f prime of x. Y dx. So that's the arc length formula, based on the Pythagorean theorem, and some stuff we know about Riemann sums, and stuff we know about the derivative. So this, like everything we've learned in calculus, needed to be applied to make this formula right there. So we have an integral. The integral has a square root. Inside the square root is 1 plus a square, and the thing we're squaring is the derivative. Lions, tigers, and bears, oh my. Okay. So the fun part is applying this. Let's see what we can do.
I don't know if I classify that as fun.
I mean, you have to reprove that.
No,
Just
you just need to know this formula right here. This is our one, right there.
Wait, is this a section over the chain rule? I mean, not chain rule, the basement parts.
No, that's still another chapter away. Yeah, I wish we had that now. All right, so we're going to try to apply this. I'm going to pick an easy situation to apply it to, relatively easy. All right, highlighter.
Your pages are out of order now.
And my pages are out of order? Right. Okay, better. Pen, color. All right, so let's try for a function. Y equals 1/2 x. Let's start off easy. Now, we want to find the arc length between 0 and 2. Now, we could just use the Pythagorean theorem for that, but we're going to try and use the arc length formula and see what it gives us. And then we'll check with the Pythagorean theorem. So the arc plane theorem says integrate as x goes from some starting point, in this case 0, to some ending point, 2 of the square root of 1 plus your derivative squared dx. So in order to do arc length, before you can do an integral, you got to do a derivative first. What is y prime here? 1/2. 1/2. Ooh, isn't that lovely? So we just drop a 1/2 in there. Clean that up a little bit. Let's see, if we clean that up, we're going to get 1/2 squared, which is a quarter. 1 plus a quarter would be 5/4. So we get the integral from 0 to 2 of the square root of 5/4. Hey, 5/4 is just a constant, right? What's the antiderivative of a constant? X times that constant. So now I get the square root of 5/4 times x evaluated from 0 to 2. Which is just twice the square root of 5/4. But isn't the square root of 5/4 the square root of 5 over the square root of 4?
Mm-hmm.
And the square root of 4 is 2.
Yes.
So this simplifies 2.
Two
square root of 5.
Or square root of 5.
Square root of 5.
It's just the square root of 5. Yeah, because this is going to be the square root of 5 is 4 times 2.
That
Square root of 4 is 2.
Oh,
so
those
with
two
that,
cancel.
you can separate.
So the answer should just be the square root of 5 according to our calculus formula.
Okay.
Double checking with the Pythagorean theorem. Pythagorean theorem says if you want the length of the diagonal, make yourself a right triangle for which that is the hypotenuse. What's the length of the base?
2.
What's the height of the triangle?
1.
1. So then this length right here is going to be the square root of 2 squared plus 1 squared, which happens to be the square root of 5. Oh, good. Our formula works.
So we just made the Pythagorean theorem, but calculus.
We made a basically a Pythagorean theorem that applies to curves.
Curves.
Yeah.
Sine.
Yeah.
And each of x also.
Yeah. So let's try it. Okay. Let's see. This one might work. Let's let y equal the sine of x. And let's let x go from, say, 0 to pi. So quick sketch of that. 0, pi. Sine goes up, sine comes down. Peaks at 1. So that's the length I want to try and find there. So to use our formula, we have to have the derivative. Okay, what's y prime here?
Cosine
Of x. And that's what goes into our formula. Formula says to find the arc length, integrate your variable from some start to some end, 0 pi, of this big old square root of 1 plus the derivative squared. So my derivative cosine of x Well, finding an antiderivative of that.
1 plus
That was
cosine
familiar.
squared.
Can you
Yeah.
explain it? What?
No, we
No,
haven't
Well,
gotten that chapter.
We know that cosine squared plus the
Is it
sine
one?
squared is equal to 1. But this is 1 plus cosine squared.
What's his name?
No,
There's
just-
nothing. How'd you say it?
it's similar but different from the Pythagorean theorem for sine and cosine. So it turns out that doesn't help. I mean, we could, so for example, let's see, and this is a good idea. So we know cosine squared plus sine squared is equal to 1. So that means the cosine squared is equal to the sine squared. 1 minus the sine squared. There we go. So I could replace that in my integral, my square root. So I had 1 plus the cosine squared. So I can now replace it with that, which is 1 minus the sine squared.
They get you.
So that gives me 2 minus the sine squared. So now I feel worse off for 2 reasons. I have a 2 and I have a minus, and I still have a square trig function. Okay, so that didn't work.
Can you break this curve?
You can't break the square root on a sum, right? So if you try to, for example, think about the square root of 9 plus 16. If you could, that would be the square root of 9 plus the square root of 16, question mark, which is 3 plus 4 or 7.
That's not.
But 9 plus 16 is what? 25. What's the square root of 25? 5. Uh-oh, 5 is not 7. Yeah, you can't break the square root on a sum or a difference. So that doesn't help either.
So we're stuck.
So we are stuck, yes. We have an integral for which we do not know an antiderivative.
So what do we do now?
Good question. We have 2 options.
Can we do use sum?
Give up.
What's that?
Can we do use sum?
We could try a use substitution. Yep. Okay, let's try that. Good page. Let's see. What should, well, let's rewrite it. So we have the integral 1 plus cosine squared of x dx. What could we let u be?
Cosine squared.
Either 1 plus cosine squared or just cosine squared. Okay, so let's try it. U equals cosine squared. Then du is equal to twice the cosine of x times its derivative, which is negative sine of x dx. And a u substitution is only useful if you see all of that sitting outside.
No, we don't.
Damn, it's not there. Okay. So that u substitution didn't work. You could try maybe u being cosine, or if you do u equals 1 plus cosine squared, you're in the same dilemma. So that didn't work. If you try letting u equal just the cosine of x, then du is negative sine, which is better than that. However, is there a negative sign hanging outside there?
No.
Nope. So that didn't work. Okay, it was a great idea, but it didn't work. Right? The trig identity was a great idea, but it didn't work. Okay. What else do we have up our tool belts? Now, how many of you do algebra first when you do one of these problems?
They do geometry.
Most of you whip out something like Desmos or GeoGebra. Isn't that true? No. All right. Why aren't we doing that?
Oh, are we?
Okay, so I'm going to go and ask a program. Now, GeoGebra and Desmos will only give me numerical values. Okay? They won't give me the actual antiderivative. However, we have a beautiful thing called the integral calculator.
But it's cheating.
It's exploring using technology. It's not cheating at this point. If it was a test and I said, do not use the integral calculator, then it would be cheating. All right, so we have the SQRT of 1 plus,
En español.
no, 1 plus parentheses cosine of x, close parentheses, square the cosine, close that. Did I do that right?
Reload page.
Yeah, that looks right. Okay, go.
Are we not going to put the
The boundaries in. I just want to see the antiderivative. Ooh,
Not be-
Ew.
capital E of x bar 1/2. What the hell is capital E?
It doesn't exist, it's like the
Another
one that we
function.
did last.
Yeah, so I mentioned this before. Integration is hard. It's harder than differentiation. Every once in a while, we come up with a function for which there is no antiderivative based on any function in existence today. Does that mean the arc length of the sine doesn't exist? It's got an arc length. It's there, right? So our only choice is to approximate it somehow. Well, we could use Riemann sums to approximate it. That's not that hard. It really isn't. We could do that. Could we take the limit of that sum? Apparently not, right? Otherwise, it would have given us a function here as the antiderivative. And that's just the way it goes sometimes.
Can you
Okay.
repeat?
So with arc length, unless the function is very carefully chosen, you're not going to be able to come up with an antiderivative. You're going to have to approximate it. Okay?
That's true.
So I will do a problem next where we can find an antiderivative, but it's just the way it goes. So now I have to say, okay, can you just give me an approximation when I put in my boundaries? So I'm going to have to say start at 0, end at pi, and go for it. And both GeoGebra and Desmos can do this second part.
How do you do approximation when pi is
You just type in pi.
like I mean, pi is also.
But yeah, pi, right, pi is another problem because its decimal goes on forever and doesn't repeat.
Wait,
So, how do you
so
do an approximation of pi?
does the computer just
It
like,
just picks a lot of decimal places.
does the computer just like go up to
Isn't it
a
like
really
0.27?
high, like,
So
Value.
the basic technique for approximating something like this is just using a Riemann sum
okay,
and picking n equals 100, then pick n equals 1,000.
okay.
And just whip it out with a spreadsheet maybe,
Mhm.
right? There are more advanced techniques that computer programs like this use to evaluate integrals, and it might be using one of those. I don't know what it's doing in the background, but they probably have documentation on it somewhere. So according to this right here, it says the approximation is about 3.82. Okay, but an exact value can't be given. It's not possible. It doesn't exist. Does that mean the number doesn't exist? No. Like think about the square root of 2. It's 1.4 blah 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 something something something. What's the exact value of the square root of 2? What's the square root of 2? What's the exact value of pi? It's pi, right? As our decimal system's limited. We can't express all of it in a lifetime. It's just math's got some weird quirks to it, and that's one of them. All right, so I could do the same thing in GeoGebra. I would just start typing int, and it said, would you like a numerical integral? I'd say yes. I say my function is sqrt of 1 plus, and I'm going to be careful by putting the cosine itself in parentheses and squaring that. And start at 0, end at pi, 3.82-ish, right? So there are just some integrals for which there is not a fundamental antiderivative, and we have to use some kind of technology to approximate it. That's life. All right, let's try another one.
Did we write just the approximation?
Yeah, so like if this were on a test, and I said show work, what I'm expecting to see is your setup and an approximation, and you could write underneath approximation by Desmos or approximation by GeoGebra or whichever tool you use. So part of the test, the next test, I'm going to have to let you use something like the integral calculator or Desmos or GeoGebra. Otherwise, there's a very limited number of problems I can ask you to give me answers for. Exact answers, at
You
least.
can use geometry for that, like in real life. This try to string out something like that.
Yeah, speaking of that, let's look at an interesting problem. So if I have, say, 2 poles, and I string a wire between them, no matter how tight you pull on that cable or wire, because that cable has weight and gravity is pulling down, it's always going to sag a little bit. The farther it is away from the point, the lower down it's going to be. So there's always going to be a slight curve anytime you try to pull something tight. Okay? It may be very hard to measure how that sag, but there's always going to be one. Did anyone ever see like a tugboat pulling something?
Yeah.
Okay, if you watch it, once they get going steady, the line is never straight. It's impossible. If you try to make it straight, it would snap before it would be completely straight, just because of gravity and tension. This curve that's formed by gravity pulling down on something like a cable or a chain is called a catenary. Or catenary, I don't know how to pronounce it, one of those things. And the graph of a catenary looks like this. Oops. And there it is. Okay. No, if I zoom in on this a little bit, does that function look familiar right there?
Wait,
Oh, that's the, is that arc sine?
That's the hyperbolic cosine.
Right there.
Cosh.
Close.
Yeah, that function right there is the hyperbolic cosine. And the hyperbolic cosine is its graph is called the catenary or catenary. Okay, so we're going to try playing with a hyperbolic cosine. So, which is that function right there. So we're going to use just a real simple one. We're going to let f of x equal e to the x plus e to the negative x over 2. So we need to know f prime of x. So dividing by 2, that's just a constant. It hangs on. So I just need the numerator. What's the derivative of e to the x?
E to the x.
E to the x. What's the derivative of e to the negative x?
Negative e to the negative.
Negative e to the x. And this function right here happens to be what's called the hyperbolic sine curve.
So cosine goes, it's the same thing as the.
Yeah, so this function right here up here is called the cosh of x. This one down here is called the sinh of x. And it's not helpful for us right now to give them those names. We're going to use the e to the x versions. All right. So remember, to find the arc length, we're going to go from -1 to 1 to find the arc length of this one. But I'm going to try and find an antiderivative here. I think I can do it. So remember, the formula is the square root of 1 plus the square of the derivative. So I'm just going to start piecing that together and doing a little algebra along the way. I'm not going to plug it in there right away. So I have the derivative, right? What's the next thing, order of operations-wise, that needs to happen? I need to square the derivative. Okay, so now we need to square e to the x minus e to the negative x. Well, that means we need to multiply it by itself and do some distributing. Okay. Let's see what we get.
I have a question.
Yep.
So, for like, or the hyperbolic cosecant, would that just be 2 over e to the x minus e to the negative x? We can just flip it, or is it a little different?
I think you just flip it, but I would have to look that up. I can't remember. I don't use these enough to remember all of their tricks. All right, so what do we get here? I get e to the x times e to the x is e to the 2x. And then the middle terms, e to the x times e to the negative x is just 1. Let's see.
Would it be e to the x times e to the negative?
Let's see, so I get, that's the e to the 2x. E to the x times e to the negative, that'd be a negative 1.
Yeah.
And then I'm going to get a negative 1 here, too. And then I'm going to get a plus, right? E to the negative 2x. So I'm going to get a minus 1, then another minus 1, then I'm going to get a plus e to the negative 2x. All over 4. That cleans up a little bit. E to negative 2x minus 1, or 2, sorry. Negative 2x all over 4.
Isn't it plus e to the negative
Oh,
2x?
plus, thank you.
So you get a negative one half?
If we put the 1/4 through everything, I think I'm gonna hold off on doing that for now. So just looking back here, so I found the derivative, I've squared it, I need to add 1 next. All right, so 1 plus that, so I'm gonna have to write the 1 as 4 over 4 to deal with that. So that just is gonna give me a plus 2 in the middle instead. Okay, so that's gonna give me e to the 2x plus 2 plus e to the negative 2x over 4. Now, boy, that's pretty similar to the square of my derivative, isn't it? Right, the square of my derivative is just this right here. And adding 1 just basically replaced the negative 2 with a positive 2. So based on that observation, I think this right here is equal to e to the x plus e to the negative x times e to the x plus e to the negative x all over 4.
Oh, yeah.
Right? Because when you multiply that out, e to the x times e to the negative x is going to give you a positive 1. And then these two multiplied give you another positive 1. So there's that positive 2 right there. So it turns out once you add 1, this right here is a perfect square, isn't it? And that's kind of nice, because what's the next step in this algebra? Square root it. Yeah, so I just want to summarize where we're at right now. Good page. We just calculated 1 plus f prime of x squared and found that it was equal to e to the x plus e to the negative x over 2 times itself. All right, isn't that what we found right here?
Yes.
Yep, that's it. And the cool thing about that is that the next thing in line is to take the square root.
Ah.
Square 15 square.
And the square root of square cancels. So now my integrand is just e to the x plus e to the negative x over 2 dx.
Isn't that, it's not, it's not.
It's
Well, it doesn't matter whether it's sinh or cosh, so forget about that for just a minute. 1/2 is just a constant, true? Okay, so that just tags along. What's the antiderivative of e to the x?
e to the x.
E to the x. What's the antiderivative of e to the negative x? Negative e to the x. So regardless of whether we call them sinh or e to the negative x, yep, sorry. Whether we call them sinh or cosh, that's irrelevant. The derivative, the antiderivative is just as easy to take as the derivative was. Now all I have to do is finish this by using the boundaries that I picked. -1 to 1. So although at first this function seemed way more complicated than like sine or something like x squared, turns out it works nice in this formula. So some functions work out nice, some don't. Hard to say. All right, so let's do this. Evaluating this, e to the 1, well that's just e, minus e to the -1, which is 1 over e, divided by 2, and then minus, plug in -1, e to the -1 would be 1 over e, minus e to the -1,
it's positive.
which is just e over 2. Let's see, if I subtract, what happens? That's going to just change the sign, so that's going to become a plus e, and that's going to become a minus 1 over e, which just matches this guy right here, doesn't it?
Yeah.
So, no, they don't cancel out, but the half goes away. Because basically what I have is I have 1/2 e plus 1/2 e, which is e. And then I have negative 1/2 1 over e plus negative 1/2 1 over e, which is just negative 1 over e. So there's the arc length, e plus negative 1 over e.
Wait, you mean minus e minus 1?
E minus 1 over e. Did I say that wrong?
You
I throw an extra negative?
Plus negative.
Plus.
Okay,
It's the same.
it's that.
Yeah.
This is the arc.
Now, that was an awful lot of work, and there's an awful lot of room for me to screw up. So how can I check to see if that's right? Desmos, integral calculator, GeoGebra, pick one.
Calculator.
What's that?
Integral calculator.
Integral calculator? Yeah, integral calculator sometimes can show steps unless it can't.
Unless it gives you.
So,
Use integral.
so let's see. It's a pretty nice tool. I recommend it. So I want my antiderivative is the SQRT, or my integrand, excuse me, 1 plus.
Do you want the boundaries?
Yeah, I'll fix that in a minute. Let's see. And then what's this? This is another parentheses, I think. E raised to the x plus, is that what I started with? No, the derivative out of minus, right?
Yes.
Minus e raised to the negative x. Okay. Close, divide by 2, close, and square it. Yep, I typed it right. Okay.
Yay.
And then close the square root. All right, and then I can give it boundaries of negative 1, 1. Go. Can it do it? It did! Oh my gosh! And it even said, yeah, the antiderivative is the sinh, which it is.
Only if we could do it.
Yeah. And show steps. Can it show steps? Not really. It says this is the cosh and the answer is the sinh. So it wasn't able to show steps. It just somebody had programmed in. This is what the sinh looks like. This is what the cosh looks
If
like.
they can do it in its head, can I do it in my head?
Yeah.
Does it follow the same?
Okay, so they got a different answer. Oh my, does that match my answer? Let's check. Let me copy that.
Can we just plug ours into Desmos and see if we got the same approximation?
Is that the same as mine?
No.
Yeah, that's
Yeah,
what I
it
would
is.
do.
Blow
X,
Because if you multiply it out, it works.
blow that up.
They technically didn't simplify the
Yeah.
answer.
So if we distribute the e to the negative 1,
Oh, yeah.
Oh, yeah.
ooh, whoa.
What is it?
If you multiply things with the same base, you add the powers. So negative 1 plus 2 is e to the 1, and then we get minus e to the negative 1, which
Okay,
is
why
1
did
over
you do
8.
that?
Yeah, so they gave us the same answer.
Because they want to write a fraction.
Because they wrote a different version of sinh. If you look back at the other way they gave me the antiderivative.
Oh.
So although they called it the sinh here, where is it? Right here, they gave this version with e's in it. So this is an alternate version of
Did ours not have e's in it?
of the sinh, or the thing we came up with. Yeah, so integral calculator is nice. Again, if you're going to enter it here, that's my f of x. I could type a g of x and call that the other function, the derivative. So 2 in the bottom, e raised to the x minus e raised to the negative x. And then down here, I could just enter my integral formula, which is n integral. And then I have to go SQRT. So you just got to type things carefully. Parentheses are important no matter which one you're using. Will it understand this notation? G of x squared. Maybe from negative 1 to 1. Hey, got the same answer. Yeah. So sometimes the integral calculator can come up with an exact answer, and sometimes it can't. It depends on the functions you're playing with. Yep.
What are antiderivative supposed to look like compared to our original function? Like, is there any way we could like make sure that we're going?
That you have the right antiderivative?
Yeah.
Yeah, so anytime you're unsure of your antiderivative, take the derivative of it and see if it gives you back what you started with. That's the only way to check. So if I wasn't sure if this right here was the antiderivative, then I would take its derivative and see if it gave me back that.
You can also graph it in decimals. And then graph.
That's the only way to go. Yeah, you can look at the graph and see if it looks like it's giving you the right slopes.
That's what I was like, well,
Yeah, you could do that graphically, but that's hard to tell. Some days I'm good at it, some days I'm not. So just graphically looking to see if one's a derivative and one's not is pretty hard. All right, let's try another one.
2 minutes.
2 minutes.
2 minutes already.
All right, let's not try another one then. Okay, so arc length, big deal. You got to know the formula. Where'd you go, formula?
Square root of
Just
1
past it?
plus
Yeah,
f of
right there.
x.
There it is right here. Yeah. So that's the formula. So, and if it's a complicated function, then my recommendation is do it in stages. Step 1, find the derivative. Step 2, square it. Step 3, add 1. Step 4, try and take the square root. Okay? Whatever you get, try and find an antiderivative. If you can't find an antiderivative, check out the integral calculator. See what it tells you. Okay? There are a few functions that we can plug into this where we'll be able to find an antiderivative with what we know so far. But if you just pick some function off the top of your head, chances are I will not be able to find an antiderivative without using technology within half an hour. And eventually, maybe after an hour, I'd be able to say there isn't one. It's just a hard problem. All right.
Test these.
So the next thing we're going to do starting tomorrow is what if we rotated one of these arc lengths? Then we get a surface. And we could find out how much paint we would need for that surface. And then how much water that thing would hold. So before we were making shot glasses, right, playing around, now we're going to figure out how much paint we need to cover them.
Well, wait,
So surface area.
So we're going to do surface area using revolutions. And it turns out the formula looks messy, but it's actually, it turns out easier to evaluate often than the arc length formula. We'll look at that tomorrow. So don't put off doing any homework today. If you're not done with washers or discs, get it done, because now you got to do arc length, and tomorrow you'll have to do surface area. Yes, it's piling up.
And
And then all the other things you have to do in your life.
I feel like I'm doing research about. We didn't even watch the house anymore because they changed the swim dates. It's on overnight. Yeah.